All right, let's lock in. So we've got two problems up here, very much like the ones we worked with yesterday. We've got a subtraction and a multiplication. So on this first one over here, what do we need to do? Yeah, we need to distribute this minus sign through, or multiply by -1. Because this is really -1 times 7 and -1 times our 8i. So this is the exact same thing as if I had our 5 minus 3i, and then we had our -7 minus 8i. Now what can we do? Combine like terms? Thank you. What like terms do we have? -3i and -8i. So what are we going to have totaled up from them? -11i. Don't lose the I. What else can we combine together? The 5 and the -7. What are they going to combine and make? -2. So for this first one, we get -2 minus 11i, or -11i minus 2. Genuinely, it doesn't matter what order you put them in. I'm going to put them in this order for calculus reasons. Yes, dear? Say it again. We have to distribute the minus sign to these two pieces. We need to subtract these. If we don't have a minus sign in the middle, that's when we're going to have to distribute everybody to everybody. So this is this chunk minus this chunk. If we need to distribute everybody, that's this chunk times this chunk. So we only need to make sure that we subtract the 7 and we subtract the 8i. So we got to distribute the minus sign. That is honestly one of the most common mistakes that I get on problems like this, is that we distribute the minus sign through, but we didn't drop the parentheses. So once we do that, with these parentheses still here, then we start distributing. It's not multiplication, it's subtraction. So be really, really careful with that. On the right one, we're going to do our distribution for everybody, because it's multiplication. So we want to have our 4 times the 2. That's going to give us 8. And we want to have our 4 times the 6i. That's going to give us 24i. We also want to take our minus I times both pieces over here. So minus I times 2 gives us a minus 2i. And minus I times 6i gives us a minus 6i squared. So when we have multiplication is when we're going to distribute everybody to everybody. Everybody in the first pair needs to multiply against everybody in the second pair. Now what can we do? Or am I done? What can we do next? Simplify the I squared is absolutely a valid option here. Because what does I squared equal? I squared equals -1. Because remember, I is the square root of -1. So if I square the square root of -1, we just get -1. So this is the exact same thing as if I had my 8 plus 24i minus 2i minus 6 times -1. Our I is the square root of -1. If I square this, I need to square this. that square root cancels out, so my I squared actually just equals the negative 1. Yeah, 100%. That's where we're headed. That's just going to make this thing be plus 6. So we really have 8 plus 24i minus 2i plus 6. Now what can we do? Add like terms. What like terms? 6 and 8. What's 8 plus 6? 14. What else can we do? My 24i minus 2i. That's going to give us 22i. It's all good. We caught it. It's all good. Sometimes we just gotta finish saying it out loud before our brain processes it. I have so been there. Why did that happen? Whatever. Do it later. My computer's being a grumpus. All right. Questions on this? Cool. So today we are gonna change gears just a little bit. We're not gonna do so many of these I's or operations on that kind of stuff. We're gonna go back to our quadratic fun. And we are gonna look at page 8. Maybe. There we go. Page 8. We are gonna talk about factoring. We've done factoring before. Yes, in Algebra 1. Like if we think about something like 8x minus 4. We could factor something out of that. I could see if there is a GCF, a greatest common factor between the two terms that we have here. What do they have in common as factors? 4. I mean, they have 2 as well, but we want the greatest one, so I could take a 4 out of both of those pieces, and I could rewrite this as 4 times. What's left over if I divide 4 out of 8x? 2x. We would have 2x. And what's left over when I divide 4 out of minus 4? Negative 1. So looking for these pieces that they share. So we start by seeing if there's a GCF. Our GCF, our greatest common factor, could be letters, could be numbers, could be both. I'm just going to write in what this means. Greatest common factor. Just in case we've forgotten what GCF is. Parentheses. So it's our greatest common factor. It's what's shared in both terms. Today we're going to work with binomials, means it's 2 terms, so it's going to be things that look like this, or they might have powers. We might have something like 8x squared minus 4x. We might just have 8x squared minus 4. We're just going to have 2 pieces, 2 terms. So there's a special pattern that applies when we have just 2 terms, and that's called our difference of perfect squares, where the front number is a perfect square and the back number is a perfect square. Everything is beautiful perfect squares. Tidy, no leftover radical stuff. So it's got to be of the structure a squared minus b squared. Or a and b are nice and tidy numbers. So something like x squared, which is a perfect square, and 9 are perfect squares because I could rewrite 9 as 3 squared. So they're perfect squares. They have to be perfect squares here. Because then what we can do is when it's written in this kind of form, we can write it in a special pattern, no factoring required, no special tools needed, because what this is going to turn into for a factored form is our a minus b and a plus b. And it doesn't matter which one goes first. I tend to think about the difference of squares having a difference and a sum. So the minus becomes the minus. And so if we had this little one I wrote in here where we thought about our x squared minus 9, which I can rewrite as x squared minus 3 squared. If I wanted to get my factored form for that one, well, I have my a being x and my b being 3. So we'd have x minus 3 and x plus 3. So we're going to take all of the pieces that we have for these first couple of terms and rewrite it so it looks like this. Whether we have x squareds or 9s or 4x squareds or 81 or whatever perfect squares we've got. We're going to rewrite them so they look like squares so that we can find our factors. And that's what we're going to work with a bunch today. So we always start by checking for a greatest common factor, seeing if there's anything that both numbers share, and then we're going to put it into factored form. Most of the ones we're going to look at today are going to be a difference of squares just because this is a pattern that's going to show up frequently for like the rest of the year and for like the rest of your math career. Difference of squares shows up a lot of places because it's a way to have quadratics that are not brutal to factor. Okay, questions on anything on this part before we start looking at some examples, aside from the one that I made up in here? Okay, so here's 1 and 2 from down below. And remember, our very, very, very first step is that we need to see if there is a greatest common factor shared between both terms. So for number 1, we've got 6x squared minus 36x. Is there a greatest common factor? Is there any number that I can divide 6 by that I also can divide 36 by? 6. Do they have anything else in common, these two pieces? Anything else they both have? An x. I can take an x out of both of those pieces. So there is a 6x inside 6x squared, and there is a 6x inside 36x. If I divide 6x out of 6x squared, what are we going to be left with? X. And if that's something that helps you to write off to the side, that is absolutely valid. We can take and think about our 6x squared being divided by 6x. Well, we can see that the 6's are going to cancel out. One of the x's is going to cancel out, and that's how we're getting left with that x. So if that's not something you can do in your head, you can absolutely write it down as a little fraction. What about 36x divided by 6x? What happens with the x's? They cancel. So what's 36 divided by 6? 6. So if I divide 6x out of this piece, we get x. And if I divide 6x out of this piece, we get 6. So we have to look and see what they have in common. And we go from there. So sometimes there might not be more work for us to do. If we have no exponents on our x's, like I don't have a squared on either of these, we're done. Huh? What was that? The intrusive thought won on that one. I don't know what was said, but 100% that was the intrusive thought came out. So sometimes we aren't going to have to do any more work than this. If we do not have exponents on our variables, we're done. There's nothing more we can factor. If you want to check and see if you are right, you could remultiply this out. If I distribute this out, I should get exactly what we started with. So if I took my 6x times x, we get 6x squared. If I take 6x times minus 6, we get 36x. So you can always check it by remultiplying it out. But that's our answer for number 1. For number 2, do they have anything in common? 49 minus 100x squared. Nope. 49 is not even, so we know it's not going to divide by 2. 49 is not, it doesn't end with a 5 or a 0, so we know it doesn't divide by 5 or by 10. 100 divides by, 2 and 5 and a whole lot of stuff. But it's all kind of built out of 2s and 5s. So they really don't have anything in common. So they don't have a greatest common factor. What do we know about 49 and 100? They are both numbers. Valid. Can we be slightly more specific about their number? They're both perfect squares. What squared gives me 49? 7. This is the same thing as having 7 squared. What squared gives me 100? 10. So if I wanted to know what squared would give me 100x squared, that would be 10x. If I take 10x times 10x, I will get 100x squared. So the square root of 100 is 10. The square root of x squared is x. That's how we can find this piece. It's got a minus in between. I still don't have this in factored form. I'm just setting it up. They do still have a minus between. I was just looking at each term individually. So to put this into factored form, we have to use our special pattern, where we have our 2 sets of parentheses. The number in the front, 7, goes in the front. 7. The number in the back, my 10x, goes in the back. 10x. Very uncommon that we're going to have x's in the back. I do not like it being the second problem here. One of these sets of parentheses is going to get a minus. One of these sets of parentheses is going to get a plus. So whenever we have these perfect square things, we are going to rewrite it as a difference of things being squared. So we're going to take stuff that has 2 perfect squares and we're going to rewrite it like this so that we can find these with minimal effort. This is our factored form. Boy. That's our answer. Like, we don't have anything else we need to do with it. This is our guide. Questions on this first one? What was that? You're very random today. In particular today, we're being particularly random. I get it, it's Friday. Like, I get it. All right, let's look at the next couple. So we've got 16x squared minus 9. Do they have anything in common? Do we have a greatest common factor? As I say, excellent thought, because it's an excellent thought because we know 9's going to divide by 3 for sure. We know 9's going to divide by 3. 16 won't though. Do you guys know the trick to see if something does divide by 3? If you add up all the numbers in the number and it divides by 3, that'll divide by 3. So like 81, if I do 8 plus 1, we get 9. Since 9 divides by 3, 81 will divide by 3. And since 1 plus 6 gives me 7, 7 does not divide by 3, 16 will not divide by 3. But it's a good thought, like totally valid. We should check and see if anything works. 16 is going to divide only by like 2 or 4 or 8. 9 does not divide by 2 or 4 or 8. So they don't really have a common factor. But it's a good idea to check anyway. Thank you. Awesome. My brain got stuck there for a second. It's all good. I'll get it down a second. I was like, they're in second period. No, they're not. They're in here. So, since we don't have a greatest common factor here, what else do we notice about these? 16x squared and 9. They're perfect squares. What squared gives me 16? 4. And what squared gives me x squared?
3.
Well, I did not ask 9. I said x squared. X. So, if I had 4x times itself, I'd get my 16x squared. Now I'm going to say what squared gives me 9? 3. So I could rewrite that piece as 3 squared. So I'm rewriting them in terms of being squared. So we're looking for essentially the square root of each piece. Then we can write it into our special pattern, where we have the 4x, and we're going to subtract the 3. And we're going to have our 4x where we add the 3. And so you can fill it in any order. If it helps you to put the parentheses there first and put it in front versus in the back, valid. If you want to do it in one row like I just did on that one, totally valid. It feels weird. So I usually fill it in the other way, but I just wanted to show you it works either way. Yes, sir.
Why couldn't we do this one like we did the rest of them?
Because this one has an x on this guy.
Oh, not an x squared?
Well,
Oh, no, because
they both have x's. Yes.
Oh.
So this only works when both of these pieces are perfect squares, or if we can write them as perfect squares. All right, let's look at number 4 here. First things first is, do we have a greatest common factor? No, we don't. This one is divisible by like 3 and 9 and stuff. This one is literally only divisible by 1 and 7. I mean, they always have a common factor of 1, but dividing out 1 doesn't help with anything, so we tend to not. But we've got perfect squares. Because what squared gives me 81x squared? 9x. If I had 9x times itself, we'd get 81x squared. So we're finding the square root of the whole chunk. And what squared gives me 49? 7. 7 squared. So I want to rewrite them like this, as they're perfect squares. Because then I can write this into my factored form, where we're going to have, using that special pattern, I'm going to put my parentheses here. The number in the front, my 9x. What was in the front stays in the front. That is my line leader. You've got to be there. What was on the caboose of this equation, the very last piece, that is going to remain as the caboose of each factor, staying in the back. One factor is going to get a minus, exactly where it came from. The other one's got to get a plus. So our factored form for our 81x squared minus 49 is 9x minus 7 and 9x plus 7. It's always going to wind up with one having a minus and one having a plus. It genuinely does not matter which order you put them in. If you want to have the plus in the front and the minus in the back, totally valid. We cannot willy-nilly switch which term is in front, though. So our line leader's got to stay the line leader on both factors. Questions on these ones? Cool, cool, cool. Schmurp. So on the next page, you've got a few more. You've got 5x squared minus 30x. What do we notice on this one? Say it louder. Yeah, we've got a greatest common factor here. 5 and 30 are both divisible by 5. So we're actually going to have a first step on this one. What? So we know 5 is divisible by 5, and we know 30 is divisible by 5. Do they have anything else in common in both of our terms? An x. They both have an x. So I could take a 5x out of this piece, and I can divide 5x out of this piece. Absolutely true. So we're going to do that. So if I take 5x out of 5x squared, what's left? What is 5x squared divided by the 5x? Just x. So if it helps, write it as a little baby fraction. That's totally okay. Because then we can see that those 5's are going to cancel out, and one of my x's is going to cancel out. What happens when we divide 30x by our 5x that we found?
6.
We get 6. Do we have any powers left on our x's? No. So we're done. When there's no more exponents, there's no more factoring. Period. If we have no powers on the x's, there is no factoring left to do. So make sure we've checked that we did it right. But if there's no more exponents on my x's, there's no more factoring I can do. If you are not convinced that you did do it right, it is absolutely okay to come through here, remultiply this together, and you can check and see if you did it right. If I was to distribute my 5x to x, we'd have our 5x squared. And if I distributed 5x to minus 6, we'd have minus 30x, which is exactly what we had up here. So you could redistribute this out to get exactly what we started with. And that's a great way to check if we're unconfident. So let's look at number 6. We've got 18x squared minus 2. They're both divisible by 2. You're right. We have a couple of even numbers. That's fine. Sometimes I just ramble. We good. They are both even numbers. They're both divisible by 2. Do they have anything else in common? Nope. What is left over when I divide 18x squared by 2? 9x squared. What is left over when I divide minus 2 by 2? 1. 0 is, as I say, 0 would be the most common mistake on that. 100%, 100%, 100%. We're like, oh, 2 over 2 cancels out, goes away. No, it's 1. That's 2 cookies for my 2 friends. Everybody gets 1 cookie. Are we done? I still have exponents on my x's. So I'm not done yet. What do we have there? 9x squared minus 1. What do we know about 9? 9 is a perfect square. Is 1 a perfect square?
Yes.
It is a number. But 1 squared is also 1. So 1 is also a perfect square. So this one has not only a GCF, but also a difference of squares. It can have both. So we have more factoring to do here. R2 is just going to sit out in front. He's an obnoxious little line leader. He's just going to sit out here. He's like that kid in kindergarten who went and stood at the door like 10 minutes early so he got to be the leader of the line. That's the 2. He's just going to chill over there for a hot minute, and everyone's going to ignore that he's sitting there. But he's that kid that was always standing at the door to be line leader. That's what the 2 is. So if I rewrite this, what squared would give me 9x squared? 3 and x. So 3x squared gives me 9x squared. And 1 squared will give me 1. So we have here a difference of squares. This is a perfect square, and this is a perfect square. So when we go to put this into our pattern, we know we're going to wind up with our 1, 2 parentheses. We are still going to have our obnoxious little line leader just sitting out front. He's just standing at the door waiting. Just doing this because he is determined to be that line leader. He's just standing there. What number is going to be in the front? The 3x. So the 3x goes in the front of each of my factors. On the back, we're going to have that 1. 1 factor gets a minus. 1 factor gets a plus. A difference of squares is always going to have 1 of each. Every single time. So we might have GCFs, we might have difference of squares, we might have both. Okay. Oh, I gotta include the 2. My screen was just askew. There we go. Okay. Questions on these binomial ones with the 2 pieces? Okay, so I am going to give you guys the last homework before fall break. Last one before fall break. So next week we are going to keep working with this because we need to do trinomials, and then we're going to start using them to solve things. Hang on just a second, Elliot. So on Monday, I am actually going to be out on a training. So I have videos recorded. I'm going to get those posted today. So if you want to work ahead over the weekend on the next part, the videos for the notes are going to be posted along with a PDF of the notes for Monday. That will be between today and Monday. That'll be the whole front. When I come back on Tuesday, we'll do what's on the back of this paper. So this is going to get us through next week. And then we'll finish up the chapter when we come back after fall break. So just as a reminder of all of the things we've got up here. So don't forget about those Canvas assignments. Those are easy points just sitting there. It's multiple choice. Like, do them.
Oh my God.
I was say, did I count? I'm so good at counting. I counted so good. Almost like I'm a math teacher or something. What?